Hello everyone. In this lesson, I'm going to go over some proofs of the derivative rules. Okay, we stated some of the rules, and then we're stepping those as facts, and off we go. So in this lesson, we're going to go over the process of how to prove those rules always work, no matter what. Okay. As known on the website, this is kind of optional. Okay, you're not going to be tested on this. Okay, but if you're going to go off and take calculus university, depending what you're hoping to do with it, you probably want to look at this at least. Okay, but I'm not going to test you on it, at least not anytime soon. Okay, that may change if we get back to school. Okay, but we'll see. But for now, yeah, this is optional. Okay, so just please enjoy the ride. Okay, so here's the first rule. Okay, and the constant rule: derivative of constants equals 0. Okay, so for all of these proofs, we're going to go back to the definition, okay, of a derivative. So if I want to do the derivative of a constant, well, it's a limit as h approaches 0 of f of x plus h minus f of x over h. But in this case, my function is a constant. So f of x plus h is c, and f of x is also c. It doesn't matter what the value of x is. It's just going to be that number over h. Okay, so that means I have 0 divided by h. Okay, 0 divided by anything. Remember, we're approaching 0, so it's okay. 0 divided by whatever h is, because it's a tiny little number, is 0. Okay, so the limit of that constant 0, right? The limit of 0 is 0, right? I'm going to be at 0, and I'm basically done. Okay, so it doesn't matter what number I started with. It cancels out in the expression, leaving me with the limit as I approach 0. Okay, and we know from our limit laws that the limit of a constant is the constant, so we get 0. Okay, and that's the whole proof. Okay, and most proofs are like this. You just fill in the expression and then try to do the same thing we did before. Get rid of this h in the denominator. Okay, our second rule is the power rule. Okay, this is an important one. X to the power n equals n times x minus 1. Sorry, x to the power of n minus 1. Okay, so we start with my expression, right? Limit as h approaches 0 of x plus h minus f of x over h. So I fill it in. Okay, I have x plus h to the n minus x to the n. Okay, now the weird part is, right, how do I expand this out if I don't actually know what the exponent is? Okay, I kind of need a general rule for this. So for those of you who have taken data management and have seen this part, okay, we're going to go to what's called the binomial theorem. Okay, and in the 3U course, you probably would have done this with Pascal's triangle. You use Pascal's triangle to expand out expressions like this. Okay, so formally, the equation looks like this. And I know it's a bit of a mess. Okay, if I have something like x plus h to the n, the expansion's in. This is n choose 0. So n choose 0, x to the n times h to the 0, n choose 1. Okay, again, just to explain what's going on here briefly, if you've never seen it before. Okay, in the 3U course, you might have seen something where, if you have like x plus y cubed, okay, you start with Pascal's triangle. So the row is 1, 3, 3, 1. Then you start with the big powers of x and count down. Okay, and then you start with the 0 powers of y and count up. This is x to the 0 y cubed. Okay, but using Pascal's triangle, these things in the brackets here, n choose 0, n choose 1, those are the different numbers in Pascal's triangle. Okay. Again, if you're taking data, you've seen this in more depth, probably. Okay, again, formally, those choose terms, this is what you're running through your calculator. Okay. So what that allows me to do is expand and simplify. Okay, that first part there. Okay, so I have n choose 0 times x to the n, right, highest power of x, and h to the power 0. The next term, next power of x, so n minus 1, then my power of h goes up by 1. Okay, and then continues down the line until I reach, right, the second last power of x, x to the 1, and the second last power of h, and finally x to the 0, h to the n. And that's minus x to the n. Okay, so a couple things here. Okay, n choose 0. Okay, if you run that through your calculator, like you plug in 3, choose 0, okay, you'll get a 1. So this first term, not surprisingly, cancels out with the last term. Okay, those cross off. Okay, now for all the other terms I have, I can reduce the exponent of h by 1. Okay, so I can cancel out all those h's, and I get left with this. Okay, limit as h goes to 0 of n choose 1, x to the n minus 1, and so on down the line. Okay, all of these terms have an h, except for the first one. So I get left with this. Okay, and again, n choose 1. Okay, maybe I'll try to explain it a little bit better. In terms of data management, what this is saying is if I have, I don't know, n objects, so like, I have 10 things in a basket, and I want to pick one of them out. Okay, how many different ways can that be done? How many different results can I end up with? Well, if there's 10 things and I'm only picking one, there's 10 ways to do that. So n choose 1 is n. Okay, and I have arrived at what I wanted. Okay. Okay, we're going to do a second proof of the product rule that doesn't use the binomial theorem. Okay, however, this does use a different form of the derivative. Okay, instead of being as h approaches 0, this is f of x minus f of a over x minus a. Okay, and this is just it's basically the same idea. Okay, if I have my function, okay, I have some general point x over here, and I would like to know about the tangent line at a. Okay, well, as x gets closer and closer and closer to a, that's just like closing that gap with h. So it gets really close and I get a tangent line. So that's what this is saying here. Okay, so I start with that. X to the n minus a to the n over x minus a. Okay, what this proof relies on is a different expansion. So I know that a is a root of the top. Okay, so I can factor this. Let me just get rid of those for a second here. Okay. The numerator becomes x minus a times this expression here, x to the n minus 1, a to the 0, x to the n minus 2, a to the 1, and so on. Okay, over x minus a. Okay, it's basically the difference of squares and difference of cubes just extends to any power, and this is what the pattern looks like. Okay, that allows me to cancel out the x minus a. Okay, and now it's saying what happens as x approaches a. So that means that I can substitute all of my x's here, become a's. Okay. When I multiply them together, I'm adding the powers. So when I multiply these two together, I do n minus 1 plus 0, so I get n minus 1. With this one, I have n minus 2 plus 1, so it becomes n minus 1. Okay, and so on down the line, they all become a to the n minus 1. Okay, how many of those do I have? Okay, well, I have n of those terms. Okay, and so therefore I get n times a to the n minus 1. Okay, so again, I know I don't have an x there, but it's the same expression. Just for any value of a, right, it's going to end up having an a there, so it's the same as having an x there. Okay. Again, if we get back to class, I can go over these again in detail and probably answer a bunch of questions about how those worked. Okay, the last one I'm going to go through is the product rule. Why do we have to do this f prime of x, g of x, and so on? Okay, so, well, I start with my limit. Okay, limit as h approaches 0. My initial function is f of x times g of x. So that's f of x plus h times g of x plus h minus f of x g of x. Okay. Now, because I'm doing this in general, it doesn't look like I can do much here. But the idea is we're going to try to split this so I can get to f of x plus h minus f of x and g of x plus h minus g of x separately so I can find the derivatives in here. So this one requires a little bit of a quote-unquote trick. Okay, in the numerator, I'm going to throw in this extra term here, which is this piece right here. Okay, I have minus f of x times g of x plus h plus f of x times g of x plus h. Okay. So because I'm adding and subtracting the same term, it's like really putting in a zero, so it doesn't affect the outcome of my expression. So I'm going to now break that apart into two pieces. Okay, f of x plus h times g of x plus h minus f of x g of x plus h. Right, split it down the middle, and there's my other limit. Right, and one of the limit laws is that the limit of a sum is the sum of the two limits, so I can do that split. Okay, for each of those two pieces, okay, I am now going to factor, right? From the first one, I can factor this, okay, and from the second one, I can factor out this. Okay, and again, I can bring that across the limits because the limit, right, of a product is equal to the product of the limits. Okay, now that I factor that out, okay, I have this, which is my expression for the derivative, right, of f. And this is the expression for the derivative of g. Okay, so that's nice. I've got that part. And then for here, well, limit as h approaches 0, h isn't involved anymore, so this is just f of x. And here, this h will go to 0, so I just have g of x. Okay, so I've got g of x times f prime of x plus f of x times g prime of x. So all I have to do is flip the order of those two, and I get the exact same expression I had at the top. Okay, so that's why we have to do f prime times g of x and f of x times g prime for the product rule. Okay. Okay. So what I might recommend, okay, for you as a challenge, maybe try to prove, say, the sum or the difference rule by yourself. See if you can go through the logic and show how the proof of that would work. Okay. All right. Thank you very much for watching. Okay. And if you have questions, let me know.